welcome back to Microeconomics. So this is the second week of choice and demand, and we will learn something about income and substitution effect and expenditure minimization. It's also we'll look at the effect on the quantity demanded when price changes for different types of goods. However, before that, I would like to show you a little bit more about the envelope theorem. I mean, I said that last week already that we will not go so much detail into this. However, while preparing for the lecture, I realized that we have quite some important application, and probably would be better to understand a bit more about how this envelope theorem works, and then we go from there. The second part of this video also will supplement a part of the thing that we derived last week, which is the indirect utility function, and we will see how to use Roy identity to revert to the Marshallian demand function from the indirect utility function, and only from the second video we go into the content of this week's lecture. So let's do it. Okay, what does envelope theorem say? So envelope theorem tells us how we can estimate the change of an objective function which we maximized when we hold these variables of it at its maximum or optimum point, and then now we vary the parameter a, which originally was kept constant. So that was the idea of the application of deriving lambda, the marginal utility of income that we did last week. But let's go now. So imagine, like before, we want to maximize a utility function u, which is a function of x1, x2, and a. However, we only maximize it with respect to x1 and x2. So a is treated as a constant at this stage. Now, so very standard approach. First, we derive the first order condition, which is the partial derivative of the objective function with respect to x1 and x2, set it equal to 0. This is the first order condition. And then we solve for solutions of x1 as some function of a, the parameter, and x2 as some function of a, right? This is what we did last week, but just with more parameters. Now for simplification, we only have a there. Now, and after solving for this, remember last week we did the indirect utility function. But actually there's a general thing when you can plug this solution into the original objective function again to arrive in something called indirect objective function. Now, in which you have u, but now let's call it v, like before the indirect utility function we also denoted v now. But now it's a function of a, which is, you plug it in the original function, right? So x1 start the function x1 of a, then x2 start function of a again, and then we rewrite a again, because a is still somewhere else in that function, right? Okay. So this is the indirect objective function, when you have the original function but now depend on a indirectly via x1 and x2 at its optimum point. Okay, so now we want to see how this objective function change when we vary a. So now we allow a to vary, to change. So very standard approach I said early. So if you want to as a minor change of one thing, when other thing change, what would you do? You take the derivative, right? So now we take the derivative of v with respect to a. Now, you take the derivative of both sides of this. How to take the derivative of this function here, the f with function of a inside. Remember, in the first week we learned something about the chain rule for the case of many variables. So here we could apply it. So that would be the derivative of the partial derivative f with respect to x1 first times outer times inner, so that is the derivative of x1 start with respect to, right? And we do the same for x2 with respect to x2 times dx2 start over dA, right? And what else? Because a is still here, so the total derivative must be plus df over dA, right? So this is the derivative of v with respect to a. How should we go from there? So now, again, keep in mind that we want to see how v changes when a changes, but x1 and x2 kept at its optimum point with the start over here. But at their optimum, at the optimum point, the first order condition hold, which says that the partial derivative, this part, is 0, right? And this also 0. So these two first terms consequently 0. At the end, what will we have? Now, we would have the derivative of v, let's write it bigger a bit, with respect to only equals the derivative of f with respect to a. So it simply tell you that even a entered this objective function, or this indirect objective function, in 3 different places. At the end, only its direct effect to the function, which is this term, matters for the change in v when it changes, when the parameter changes. And we can ignore this indirect effect via other variables. So that's why at the end of last week's lecture, you could derive the marginal utility of income. Now, or v, actually here it should be v, okay, which is lambda. Now, and thanks to this envelope theorem, we could, you will see later, derive a lot of derivative with respect to a parameter without having so much trouble with these indirect effects inside. Now let's talk about Roy's identity, which will tell us how we can derive or revert back to the Marshallian demand functions when we are given only the indirect utility function. So imagine this is the indirect objective function, the Lagrange, the indirect Lagrange, where we plug in all the solution for x1 and x2 inside already. So now, remember, when we derived the lambda, we had already the derivative of u with respect to income, which is also the derivative of L with respect to income, equal lambda. That's where we stopped last week, right? And now let's denote it as 1. Similarly, you can also take the derivative of u with respect to P1. What will we have? Where do we have P1 over here? Here, right? So that is lambda times x1 start. Let's write it explicitly here as P1, P2, and I, which we just solved from the first order condition. Okay, let's 2. Now think about it. What if we divide 2 by 1? Lambda will be gone, right? It will be simplified. So let's do it now. Here. Will be times x1 start P1, P2, I over lambda. And at the end it is x1 start P1, P2, I, right? And you might ask yourself already, how about P1 in these places, nah? When you take the derivative? How about the P1 implicit in x1 and also here? Thanks to envelope theorem, we can ignore them, and we could keep these x stars at optimum value. So that's how we could write into this. So in summary, Roy's identity tells you that you could arrive in the Marshallian demand function by taking the derivative of, like the ratio of these two derivatives. But now you start, which is V over P1, and then in the denominator you have the derivative of V with respect to I, right? I missed something here. Here it should be minus, right? Because here is minus. So if you take this derivative of this, that will be minus over here. So consequently, you must have a minus. This is too ugly. Over there.